Hello everyone, let's take a look at our next problem. Determine all pairs m and n of positive integers satisfying two of the digits of m are the same as the corresponding digits of n, while the other digit of m is one less than the corresponding digit of n, as in, say, 263 and 273. So that's one condition. Both m and n are 3-digit squares. Okay. And then there are some hints given in this question. Actually, I'm going to skip the hints for now. I might come back and read those in a second. Okay, so m and n are 3-digit squares. And two digits are the same. The other is off by 1. So how many 3-digit squares are there? So 10 squared is 100. 20 squared is 400. 30 squared is 900. What's 31 squared? It'll be 961. So there's not even that many 3-digit squares. Although I want to do something perhaps a little bit more clever than brute forcing this. So let's think about A and B, where so A and B have to be integers between 10 and 31. So these automatically will both be 3-digit squares. And then the difference between them, a squared minus b squared, will have to be a multiple of 10, right? So if two of the digits are the same, let's just assume that a is greater than b. Two of the digits are the same. This will have to equal a multiple of 10. Or a multiple of 100, or be, less than 10. Well, I think we can rule out right away that a squared minus b squared is less than 10, right? The smallest that this difference can possibly be is 21, when a is 11 and b is 10. And we need here for k between 1 and 9. No, we don't. We need k to be equal to 1, don't we? Because the difference, the difference between the different digit is only 1. So k equals 1. Let me go. Okay, so this is equal to 10 or 100. Okay, well, I look at this and I think to myself, let's factor the left-hand side as the difference of squares. A plus b times a minus b is equal to 10 or 100. I don't think we're going to get anything where the difference is equal to 10. And to see that, maybe we can even just factor 10, which is, of course, equal to either 10 times 1 or 5 times 2. But even so, I've already said the smallest difference between any two squares in this range is 21. So this can't possibly happen. So we can get rid of that. Okay, so we have that the difference between our squares has to be 100. So we're looking for 3-digit squares that differ by exactly 100. Can I think of any off the top of my head? I don't really know the squares above like 12. Okay, so what could we do here? We could try and consider the factors of 100 and set up some equations for a and b such that a plus b and a minus b are factors of 100. And remember, we've said a and b are integers between 10 and 31. So then a plus b is less than or equal to 41. So we're thinking of factors of 100 that are less than, we have to think like 25 and 4, right? What are the factors of 100? 100, 50, 25, 10, 5, 2, and I guess we have also 4, 20, I'm going to take a stab and just go, well, I guess the only combinations that could possibly work are 25 and 4 and 5 and 20 in this equation here. So let's go a plus b is equal to 25 and a minus b is equal to 4 and see if we can get something here. Let's add the equations together. So 2a is equal to, okay, this immediately breaks. 2a is equal to 29. So that doesn't have an integer solution for a. And the same thing would happen if we used 20 and 5. So am I missing something? I'm going to take a quick look at this hint that they give. Find as efficiently as possible all pairs of positive integers satisfying 2 of the digits of m are the same as the corresponding digits of n. The other 2 digits of m are both 1 less. Okay, the hint is actually not a hint at all. The hint just gives us a more complicated problem, which, sure, solving that might give us the answer to this one. I'm not sure if there are any solutions to this. Right, if they differ in the tens digit, then the difference, that's not possible. If they differ in the hundreds digit, so 2 3-digit squares that differ by 100. 2 squares that differ by 100. So the difference of the squares is factored. They both have to be factors of 100. And they either a and b, so if we look at this, a and b have to either both be even or both be odd. And that would make a plus b and a minus b would then also have the same parity. They'd be either both even or both odd. But if we look at how, when you factor the number 100, that just doesn't happen. I mean, 50 times 2, sure, but that's out of the range of our numbers. That doesn't work. That doesn't work. I think there's no answer. No, there are no solutions to this. I mean, that would be my conclusion here. if I wasn't allowed to brute force it and write out all of the 3-digit squares. So what I'm going to do is I'm going to say that that's my answer, that there are no 3-digit squares that satisfy this condition. But check the description, because what I'm going to do is just list out all the 3-digit squares. And if I happen to find that there are 2, I don't know what would be wrong with my solution here, but I'll update you in the description. Thanks for watching. I am so stupid. Very stupid. So 24 squared is equal to 576, and 26 squared is equal to 676. So this is the answer. So I'd like to at least talk a little bit about why my solution previously didn't end up working. It would have worked. This would have been completely correct. But for some reason, when I considered the factorization of 100 as being 50 times 2, for some reason, because I had written this down, I thought that 50 was too large for a plus b to be equal to 50. I was thinking the largest value of a plus b we could get is 41. But that's clearly not true. If a and b are both large, close to 31, then a plus b is certainly going to be greater than or equal to 50. So I'm going to sort of pick up from this part of my solution and show how the rest of it would properly have worked. And in fact, the argument I had earlier about the parity of a and b shows that 50 times 2 is the only factorization of 100, which would end up working here. So we would need a plus b to be equal to 50 and a minus b to be equal to 2. This gives us immediately that 2a is equal to 52, or a is equal to 26, which gives us b is equal to 24. So the two numbers we're looking for, the 3-digit squares with this property, are 576 and 676. Thanks for watching.